now discuss the twin of electricity, which is known as magnetism. Intuitively, you may think that electric force and magnetic force are one of the same thing. Let us start our journey in this topic as we explore the origin of magnetism. It can be proven that a moving charge creates a magnetic field. According to kinetic molecular theory, atoms vibrate in response to thermal energy. Therefore, we can say that all of us generates a magnetic field since our temperature is above the absolute temperature where all vibrations have ceased. Magnetic moment arises when a charge travels in a closed area. We can say that even the hydrogen atom has a magnetic moment, because the hydrogen atom has one electron that revolves around the nucleus. Therefore, we can say that the movement of the electron in a closed loop creates a magnetic moment. The magnetic moment generated by the electron is given by the formula mu is equal to I times A. A is said to be the area of the orbit. I is equal to the current. We can now rewrite the equation above as mu is equal to Q over T multiplied by A. We all know that the electron is moving with a certain velocity, v. The electron completes its revolution in a specific time frame known to be the period. We use the variable t to denote the period of motion. Knowing the velocity v of the electron is equal to the distance traveled by the electron, which is equal to the orbit or to the circumference of the hydrogen atom, which is equal to 2 pi r divided by the time or the period t. We can solve for the period t and find out that this is equal to 2 pi r over v. The frequency is the inverse of period t. This is equal to 1 over t, which is equal to v over 2 pi r. Therefore, it goes to show that the magnetic moment, mu, is equal to I, A equal to Q over T times A is equal to E times V over 2 pi r times pi r squared. We now simplify the equation and find out that the magnetic moment mu is just equal to E times V times r over 2. The magnetic moment is related to the angular momentum of the electron. The angular momentum of the electron is denoted by L. This is equal to the mass of the electron multiplied by the velocity and the radius of the hydrogen atom. We can solve for r. We can see that r is equal to L over m times v. We can substitute this to our formula for the magnetic moment mu, which is equal to E times v times r over 2. Since we know that r is equal to L over mv, we plug it in. The resulting equation is mu is equal to E times the angular momentum L over 2 times m. In quantum mechanics, the angular momentum is a fundamental quantity and it has an equivalent formula equal to h over 2 pi, where h is the Planck's constant. We substitute the formula for L in our previous equation and find out that the magnetic moment of the hydrogen atom, also called as Bohr magneton, read as mu sub b, is equal to E times h over 4 pi times m. The electron also has its intrinsic property, called as spin. This is analogous to the way how the Earth rotates on its axis. This is also related to a magnetic moment, which is almost equal to that of 1 Bohr magneton, 1.001 Bohr magneton. The uniqueness of the magnetic moment per atom is the reason why some materials are easily magnetized while some are not. We now formally introduce the types of magnetism. As mentioned earlier, magnetic behavior depends on the orientation and distribution of electrons in the atom. The first classification of material according to their magnetic property is known as paramagnetism. In most materials, their magnetic moment is up to 0. However, in some cases the atom has a magnetic moment that is in the order of the Bohr magneton. When such a material is placed in the presence of an external magnetic field B, the field exerts a torque on each magnetic moment, causing the magnetic moments to align. The additional magnetic field contributed by the material is proportional to the magnetic moment caused by the electron. The total magnetic moment of the material per unit volume is called as the vector quantity known as magnetization of the material, denoted by m, which is equal to the total magnetic moment divided by the volume V of the material. We can compute for the additional magnetic field of the material. This is denoted by B sub p, which is equal to mu sub 0 multiplied by the magnetization of the material, m. If such a material surrounds the current-carrying conductor, the total magnetic field produced by this interaction is given by magnetic field B is equal to the original magnetic field B plus mu sub 0. Such a material is called a paramagnetic material. The magnetic field of the material is enhanced by a dimensionless factor K sub m. This is known as relative permeability. The value of the relative permeability is different for different materials. For common paramagnetic solids and liquids at room temperature, typically ranges from 1.00001 to 1.003. The magnetic permeability, denoted by mu, is given by the formula mu is equal to K sub m times mu sub 0. Magnetic susceptibility of a material is the difference between the magnetic permeability and unity. This is given by the formula X sub m is equal to K sub m minus 1. This is also a dimensionless quantity. The tendency of magnetic moments is to align themselves parallel to the magnetic field where the potential energy is minimum. However, we know that thermal energy, heat, tends to randomize the motion of particles, electrons, and of course of atoms. For this reason, magnetic susceptibility tends to decrease with increasing temperature. The law relating temperature to magnetism is called Curie's law. It is described as follows: the magnetization m is inversely proportional to the absolute temperature. This can be expressed using the formula m is equal to c times b over t. This relationship is called Curie's law, after its discoverer, Pierre Curie, 1859 to 1906. The quantity C is a constant, different for different materials, called the Curie constant. The second type of magnetism is called diamagnetism. Some materials have magnetic effects because an external field alters electron motions within the atoms, causing additional current loops and induced magnetic dipoles comparable to the induced electric dipoles. In this case, the additional field caused by these current loops is always opposite in direction to that of the external field. An induced current always tends to cancel the field change that caused it. Such materials are said to be diamagnetic. They always have negative susceptibility and relative permeability slightly less than unity, typically of the order of 0.99990 to 0.99999 for solids and liquids. Diamagnetic susceptibilities are very nearly temperature independent. The third type of magnetism is called ferromagnetism. Ferromagnetic materials that includes iron, nickel, cobalt, and many alloys containing these elements. In these materials, Strong interactions between atomic magnetic moments cause them to line up parallel to each other in regions called magnetic domains, even when no external field is present. The total magnetic moment of a domain may be many thousands of Bohr magnetons. The torques that tend to align the domains with an external field are much stronger than occur with paramagnetic materials. The relative permeability is much larger than unity, typically of the order of 1,000 to 100,000. As a result, an object made of a ferromagnetic material such as iron is strongly magnetized by the field from a permanent magnet and is attracted to the magnet. It is quite obvious that a magnetic field present has an effect to moving charge. If we have a moving charge or a stream of moving charges, we therefore have a current. The net effect of an external magnetic field B on a charge depends on four factors. Magnitude of the charge. Strength of the external magnetic field B. Particle's velocity. The force is perpendicular to both B and V. If the charge is at rest, it experiences zero force. The force resulting from the interaction of the moving charges to the present magnetic field is given by F is equal to Q times velocity V times the magnitude of the present magnetic field. The formula given above is not deduced theoretically but was formulated through experiments. It is a product of our observation to the said phenomena. We use the right-hand rule to tell the direction of the force in the charged particle. The right-hand rule states that, to determine the direction of the magnetic force on a positive moving charge, point your right thumb in the direction of the velocity, v, your index finger in the direction of the magnetic field, b, and your middle finger will point in the direction of the resulting magnetic force. We now introduce the units of magnetic field. The unit used to quantify magnetic field is called Tesla, in the honor of Nikola Tesla, 1856 to 1943. The unit must be the same as the units of F over Q, V, therefore, the SI unit for B is 1 Newton times seconds over coulombs times meters. But since define the ampere as 1 coulombs per second, we can write 1 Tesla is equal to 1 Newton per ampere times meter. Another units used is called as Gauss. This is in the honor of the eminent mathematician and physicist, Carl Friedrich Gauss, 1777 to 1855. 1 G is equal to 10 to the negative 4 Tesla. We can visualize the presence of magnetic field by drawing magnetic field lines. We can represent any magnetic field by magnetic field lines, just as we did for the Earth's magnetic field. The idea is the same as for the electric field lines. We draw the line so that the line through any point is tangent to the magnetic field vector at that point. Just as with electric field lines, we draw only a few representative lines, otherwise, the lines would fill up all of space. Where adjacent field lines are close together, the field magnitude is large.